Ben Koifman, who holds degrees in electrical and civil engineering, and is currently a visiting faculty member at the Newcastle University and a professor at the Ohio State University in the USA. He has dedicated years in pursuit of accurate traffic flow data on how people drive, and this included extracting more information from conventional traffic detectors, working with emerging technologies, and developing new tools to measure traffic flows. We will now proceed to the presentation. Please welcome.
All right. Thank you for having me here today. Hopefully, can you hear me in the back of the room? Okay. So, on the one hand, I will be talking to you about traffic flow theory and advances found in unexpected places, but then also, especially a good lesson for students in the room, is, just because everyone says this is how it's done and this is how it works, it doesn't hurt to always go through life being a little suspicious. But we'll get to that in a few minutes. So, I'm going to be talking to you about the fundamental relationship, which, if you haven't spent years staring at traffic, you might go, what the heck is a fundamental relationship? So, on the roadway, you can talk about traffic in terms of how fast the cars are going, speed, how many vehicles per unit time. So I might watch out the window, I might see 10 cars go by in 30 seconds, so that's going to give me my flow. And I could also talk about traffic in terms of how many vehicles per distance, so maybe 50 vehicles per kilometer. So if I walk along the road or I look at a picture and I just count how many cars over space, that gives me density. Collectively, these three measures are the traffic state. So you abbreviate flow with Q, that comes from queuing theory, K for density, that comes from German for concentration, and V for velocity, and that comes from V for velocity. So with the traffic state, if I told you any two of these, I could derive the third, or at least that's, there. If you guys want to argue semantics about second order factors, that will be my next talk if you want that. But almost all the theories we have for whether it be how do individual drivers drive on the roadway, or if you watch the roadway, you'll see signals and disturbances propagate through the roadway. Almost all of those are going to be based on the fundamental relationship that relates the three, Q, K, and V together. So for example, when you go out and you look at, well, for those of you who drive, or if you don't drive, you ride on a bus at some point, you come up to a red light, you stop. Light turns green, there are 5 cars ahead of you. You don't pull out right away, you gotta wait for the first car to move, and then the second car to move, and so forth. But when the first car moves, and then the second car moves, that creates a backwards moving signal. So that's one of the easiest ways where you can sort of envision signals and waves in the roadway. So these theories that are based on the fundamental relationship, those are at the core of traffic simulation and modeling. And then you range from real-time traffic control, when does a light need to be green to serve the traffic most efficiently, to long-term urban planning, where are we going to put that stadium 20 years from now? So they all have little bits and pieces of the traffic flow theory that comes to them. So we're going to go out to this little shop somewhere in the backwoods of Ohio, USA, in 1935. Green Shields playing with cameras. I think he's taking pictures 1 frame a second, which is incredible high speed for 1935. And he's just taking pictures of a roadway as cars are going by. From that, he's tabulating speed. The vehicle traveled this much distance between frames. And then I think he measured density rather than flow, but he measured 1, and then he used numerical analysis. He just used conservation of units to derive flow from density and speed, and that was the first use of fundamental relationship. And then, as I said, dimensional analysis to derive density from flow. Nowadays, we'll commonly, so paper, blackboards, and so forth tend to be 2-dimensional. We got a 3-dimensional relationship, so we'll take a slice through that 3D space and either talk about speed versus flow, flow versus density, or speed versus density. And again, given any 2 of those, you can derive the third just through multiplication. So, not quite 20 years later, Wardrop comes along. And it's like, looking at all of these vehicle trajectories in space, we really need to be a little bit more quantified about what we do. And so that brought a little bit more, building on the past. He's brought a little bit more of an analytical approach and showed, biggest thing is just the speeds over time. So if I sat out here, I measured the speed of every single vehicle go by, and someone stood on top of the building across the street and measured the speed of every single vehicle at this instant along the roadway, we'd get different numbers. And showed that if you want to use the fundamental relationship Q equals KV, that you need to take the average speed over space rather than the average speed over time. Little tiny semantics that if you're not in the thick of it, it's like, okay, well, who cares? But the trouble is a lot of people who are in the thick of it don't even remember that. But that's, that is not the topic of today's talk. But Q equals KV, the important thing there is you use a spatial space average of speed. So then, only a couple of years later in this case, so 2 or 3 years later, Plato, Witham, and Richards gave birth to the hydrodynamic models. Here, very simple, speed of the disturbance, U, is delta Q over delta K. Say what? What it is. So we come and we look at the roadway. Everything's right now in this pretty green traffic state. Here's our fundamental relationship. We're assuming that all traffic states possible are going to be on this curve. And remember I said if I give you flow and density, you get velocity. Where's velocity on this plot? It's the slope. So this slope, highest slope you got, that's the fastest. The more you go down, lower slope, lower speed. So this state is close to capacity, so it's high flow, and it's at your highest speed. And so that's what we see across the entire roadway measured in distance. And this is a time-space diagram. And up to this instant in time, we got that traffic state. But then something goes wrong right here. There's an accident maybe that's blocking a lane. Upstream of this, downstream of this blockage, we drop to a lower flow, but we keep the same speed. And that's this region. And that's slowly propagating downstream. Meanwhile, upstream of this blockage, conservation of flow says we can't get more vehicles through than this, so we stay at the same flow, but we're now over on the congested regime at a slower speed. So we're seeing a queue build up right there. And that keeps going over time, so as we get further in time, we can see, okay, this low flow, free flow, low flow, congested, and what was previously high flow, high speed. So this is where the delta Q, delta K comes in. So the interface between these 2 points on this graph, horizontal line, we come into the space plane, horizontal line. It's not moving in time, it's not moving in space. The interface from these 2 traffic states, negative slope, and we see that right here, the U2. So this is the Q growing backwards, and then this is the discharging traffic going from this state to that state at that slope. So that's LWR, Lighthill, Witham, and Richards in a nutshell. Okay, now we know what delta Q over delta K is. A couple more years later, it's like, well, now wait a second. Density is vehicles per mile. If I flip that over, I can instead say miles per vehicle, but we'll talk about in feet per vehicle. Feet per vehicle. So that's now giving you spacing. You can also take flow and invert it, and you get time per vehicle. So now you take the macroscopic models, and you talk about them. So you macroscopic, many vehicles, flow, density. Flip them over, you get space per vehicle, time per vehicle, and that's going to give you your microscopic models from the individual vehicle perspective. And so this gives you a 4th permutation of representing the fundamental relationship. so the speed spacing curve. They're all showing you roughly the same thing, just different perspectives slicing the numbers. And one of the big things is they take the form, your car following models, the microscopic models, are taking the form of how does the following vehicle respond to its leader. Now, if you sit and you stare at this stuff long enough, you'll go, well, LWR, Lytle, Witham, and Richards, great stuff. It tells you how the waves propagate, but no matter how you twist it and turn it, it will not tell you how waves form. So a lot of mathematicians come over here and go, well, if you take the second derivative or the third derivative or so forth, you get disturbances forming. So there's a whole other family of folks who it's like, well, you just take the higher order derivative of the fundamental relationship and that will then induce waves and disturbances. But now we look at this mighty castle, and it took 20 years to go from, oh, there is a relationship to this is how we work with it mathematically. And then when we got to these theories in the 50s, it still took another 30 or so years before we had actual large quantities of data that you could work with this stuff. So 50 years, most people will have come and retired and so forth. So by the time the researchers were able to actually have data where they could work with this in large quantities, it's been taken as a given, all of this stuff. So you wind up even to this day where you've got people playing with the numbers going, okay, well now this is how I shave this off or I make this look pretty, but no one's questioning the basic fundamental assumptions that go into any of this stuff. I love this quote, 1963, what is that, 50 years ago? Still true to this day. You got everyone who's working in traffic flow theory, it's like, okay, I've got my theory, now let me go prove it. And there are not many people going, okay, here are these data, what is going on? What do these data show us? And as I mentioned, nobody even stops to question the fundamental relationship besides what shape it should be. This one is one of my favorite representations of the fundamental relationship. So this is empirically based, flow versus density. It's got this nice curve and it's sweeping gently when it gets to the top, and then it's got this sharp, steep drop. Okay, that will create fast-moving waves, and then it slows down, and you just beautiful. It's like a gentle roller coaster. It's got this lovely form, lovely shape, and it is so completely wrong. So this comes out of the physics literature. Physicists love to write these 2-page papers. It's like, okay, here's my 2-page idea. Here's my next 2-page idea building off of this. So you got to dig through like 20 papers to figure out where this thing came from. And the fundamental underlying assumptions in this are wrong. So it's using short-term data that gives you nice high spike in the free flow regime due to tailgaters. They're assuming, okay, well, we've got 2 different lanes where we'll assume both lanes are the same when they aren't, and so on and so forth. But even if this were a correct curve, this is the problem. This is real data. Can anyone fit a curve, anyone in this room fit a curve to those data that's representative of all of those data? If you do, if they don't give you a PhD here, come with me, I'll give you a postdoc position. That's real data. So you got all of these theoreticians sitting here going, okay, well, which curve is which and which is best? But you got all this stinking noise. So obvious solution is you go to microscopic data. What are the individual drivers actually doing? And these data are great when you can get them, but they only exist in small quantities. And then you got the macroscopic data. So vehicles per unit time. So that's typically going to be from your detector. I saw 20 vehicles in 30 seconds. Of course, you express it in vehicles per hour, so it turns into 1,600 vehicles per hour over this 30-second period. But that's what you're dealing with from loop detectors. And now this is where being a student, perhaps you haven't learned this yet, but loop detectors suck. So that gives us a problem. We need to address the data before we talk about the relationship. And to do that, we're going to need a lot of data. Now, if we need a lot of data, do we have any choice but loop detectors? Well, there are now sensors out there that emulate loop detectors, but they're still essentially, their analysis is the same as what you get from a loop detector. They just use a slightly different sensing technology. So if we don't have any choice about loop detectors, why don't we go back and just ask, do loop detectors really suck? Now, of course, if you don't even know what a loop detector is, this should be the first question. What the heck is a loop detector? So typically, loop detectors are either embedded under the pavement, or if they're retrofit, they'll come out with a saw and they will cut a shape. In this case, they're cutting a diamond shape. They could be square shaped, they could be round, all sorts of crazy shapes. But they cut a shape, cut a groove in the pavement, stuff wires in, put epoxy over it, cut in lead lines, run it up to electronics running in this cabinet, and it's just basically a metal detector in the roadway. You put a piece of metal over it, it goes on, turned on. You take the piece of metal off, on, turned off. And it does that anywhere between 60 hertz to 1,000 hertz, so many times per second. So from this alone, you could tell there's a vehicle or there's not a vehicle. So every time you switch between not vehicle to vehicle, that gives you a count of one vehicle. Do that over an hour or about 30 seconds, that tells you your flow. If you have two of them, you can measure the travel time between the two and you get speed. You can also calculate vehicle length. So now we go back to 1969. This research was actually working with optical detectors. And just quoting from their paper, the printing of this detector data was done only every 6th observation period, that is every 30 seconds. And as is so often the case, first person who does it sets the standard that everyone else follows. So it's pretty much still the norm to this day. What they did in 1969 out of convenience, we now do, we take it as gospel. This is as written as we should always do it. So we just arbitrarily, every 30 seconds, we say, we're starting a new sample. Tell me how many vehicles pass between here and there. Okay, that's my flow. And then occupancy. With the loop detector, you can't really measure density, so we use occupancy as a proxy for density. So that's the percentage time that the detector is on. But it's like density, and I'll show you some of that here in a little bit. So the big problem with this sampling technique is there's so many confounding factors that can enter in and change your flow relative to occupancy or speed or so forth. And so I'm going to talk about some of those here in the next few slides. So the fixed period averaging, conventional practice, introduces huge errors. And very few people have appreciated those. So a very simple one, suppose we have a very regular pattern of vehicle arrivals. The detector turns on, and it stays on for this amount of time, then it turns off, turns back on, and so forth. And we've got a fixed sample period of 30 seconds. If we start our sample period here, we count that rising time, we, in this case, would get 720 vehicles per hour. But if we're just 1 second later, and we turn on after that vehicle turns on, and then our sample period starts, all of a sudden our flow drops 120 vehicles per hour. Bang, zoom, 1 second difference. Then if we look at the other end of the, so if we have more on time than off, or vice versa, just depending on small little difference. So these first two have more on time than they have off, and these last two curves have more off time than on. We can see a change of 10% occupancy right there. So just what happens at the tail ends of your sample period could be 10% difference in your measurements. Never even thought about that. You go look at just about any paper on traffic flow, and they will show you a curve. Now, if you have passenger cars, you're going to get this blue curve. So you got jam density out here, so that's the number of vehicles you get when everyone pulls up as close as they're going to pull up to the vehicle in front of them at a complete stop. And then you got whatever your maximum flow is. You call that capacity. and so forth. That's good for passenger cars, but if you have single unit trucks, your jam density is much smaller, your capacity is much smaller simply because the vehicles are larger. And if you get multi-unit trucks, even smaller. No one even stops anything. This is just 3 curves. Reality, you're going to have a mix of vehicles and traffic. So, not even getting into, well, should it be 1 curve or a cloud of points? This is another huge source of noise that no one deals with in the raw data. Related to that, so that slide was just if you had all cars or all trucks of either different types. Now, at low flow and congestion, you got a 30-second sample, you might have flow of 900 vehicles per hour, but that still could only be 3 or 4 vehicles per 30 seconds. So if you have 3 cars, you'll get 1 occupancy. If you have 1 truck and 2 cars, you'll get a very different occupancy for the same speed and flow. So mixing in inhomogeneous vehicles, again, even controlling for the edge effects, gives you very different measures. So all of these sources of noise go into that 30-second sample and just mask anything and everything that you care about. So sitting down, thinking about all of those issues, we came up with a single vehicle passage method. So 1 vehicle goes by, and we just say, okay, rear bumper of 1 vehicle to rear bumper of the next vehicle, we got 1 vehicle for whatever that time is. So our flow, our sampling period is now dynamic. That gives us a measure of flow. Our occupancy, we take however much time the detector's on, calculate occupancy, speed, and vehicle length similar ways. So we're now taking the measurements on a vehicle-by-vehicle basis. So this approach gets rid of the partial headway problems, and then we can group vehicles by similar lengths and similar speeds before aggregation. And then, at low flow conditions where you only have 2 vehicles per 30 seconds, we can control for that and still get a large sample just by saying, okay, if the bin has fewer than 100 vehicles, let's not work with it. So here we go, conventional 30-second data, single vehicle passage data. Much cleaner, right? Anybody out there? Much cleaner, right? Wow. The secret's in the sauce. So first step is we take this big mess of points and we divide it by speed. So divide it by vehicle length. So these are the shortest vehicles, 0 to 16 feet. So the 0-foot vehicles are probably errors. These are the most common ones, the passenger vehicles, 18 to 22 feet. I'm skipping a few bins there. I'm skipping a lot of bins here. And here are the longest vehicles, the trucks. So as it is, you can already see a distinct difference, low slope, high slope. And that's emerging just because of the vehicle length at free speed. Then for each of these length bins, we come and we sort it again by speed. So this is the high speed, and again, skipping many steps. So high speed, some speed in the middle, some speed down below. So these are about 1 mile an hour speed bins. So we're now getting these slices. From these slices, we take the median flow, median occupancy. That gives us the red points. All right. Everyone sitting down? All right, brace yourself. Boom! Right there. That's a pretty clean curve, right? There's no smoothing, no averaging. Well, there's this averaging, but this curve just falls right out of these medians from the bins. So this curve emerges on its own from these data. This bin is completely independent of that bin and completely independent of that. And this is a single day of data. This is looking at the passenger vehicles. So by doing away with all those sources of noise, we now have homogeneous vehicles. We don't have the partial sampling effects and so forth. We get nice, clean relationships. So here, now going to 12 million vehicle observations, so this is over many days, many detectors, we get this family of curves. And you need to do this because 90% of your vehicles are passenger vehicles. The slower a vehicle goes, the less likely it is to pass over your detector when it's moving slow. So if you want to start getting data points for the long vehicles, the green ones right here at the bottom, and you want them slow, you're going to need a large sample size. So we take a large quantity of individual vehicle observations and we get that. Now, remember I said occupancy is often used as a proxy for density. That is true, but that proxy only goes so far. And you've got people who want to come in and use passenger car equivalents. So you say, I've got this occupancy, multiply it by this constant, and that gives me density. That only works if you always have exactly the same number of trucks. But with this method, all of these vehicles are the same vehicle length. So now I can actually use a direct calculation to go from occupancy to density. So I got these measures from a point detector, and I can still get a measure of density that's accurate. There are people who like to skirt around this and say, well, I'll calculate density from flow and speed. You can do that, but you're just masking the fact that you've got a length dependency in that calculation. So again, because now all of the vehicles are the same length, before I do this calculation, I can do it, and I can do it properly. All right, now here's the really cool thing. I can go from these macroscopic relationships now to individual vehicle level relationships, because average spacing is just the inverse of density. So I get to here, and so I see different curves for different vehicle lengths, and they're all nice and well. The passenger vehicles in the next longer vehicle bin, lots of those. The longest vehicle bin, the semi-trailer trucks, also lots of those. In between, these are still sparsely populated, so they're a little bit more noisy. Maybe you gotta go to 20 million or 50 million to get those all nice and clean. But really, loop detectors suck, and these trends are just some artifact of my calculations, right? Come on, say it with me, loop detectors suck. Well, so NGSim, these guys, they stood on top of a building, videotaped traffic from 8 different cameras, went, okay, this vehicle's here in this frame, now it's here in this frame, now it's here in this frame, and so they constructed individual vehicle trajectories, tracing out where a couple thousand vehicles went. So taking those individual the vehicle trajectories from NGSim, I start here with the speed spacing and back calculate, and lo and behold, I get similar looking plots when I start with what little microscopic data there is out there. Huh. Okay, maybe I'll believe you that loop detectors are okay. All right, very, very long preamble. What the heck's the question again? Well, I told you this conceptually ages ago, that, okay, we got the short vehicles, you're going to have one jam density, and the long vehicles, you got a different jam density. This is a truism, but no one pays any attention to this. So right there, I have the trivial finding of this research. You can fit fewer long vehicles in the same space that you can fit short vehicles. So you fit many more short vehicles in the same space that takes the long vehicles to occupy, and so you get a lower jam density for the long vehicles. This isn't widely shown, isn't widely used, but, you know, well, duh, that's an obvious conclusion. Yes. But now look again. All right, this is perhaps my last special effect for the day. So I got this slope, and now as I move over here, it gets steeper. You see how my arm is getting a steeper slope? Steeper slope means faster. So here, if I go from this state to that state, perhaps I see the signal propagate upstream at 12 miles an hour. But if I go from this state to that state on the semi-trailer trucks, maybe it propagates upstream at 18 miles an hour. That, for as trivial as it may seem, is frickin' rocket science. Well, or at least it's frickin' innovative. But this too, once I explain it, it's like, okay, you know, so this is one of those sort of light bulb moments. You wouldn't think about this until you see it, but once you see it, it's go, oh yeah, the trucks are a lot less compressible. So as these vehicles start moving, they'll take a gap larger than the gap the passenger cars will take, but you've only got one gap where you might have 5 or 6 gaps between the passenger cars. So when these start slowing down, they're going to close all of these gaps and store more energy, and so the disturbances are going to propagate slower than they will through the trucks. I know, it's like if you're not looking at traffic, so what? Well, the what is, the impacts of inhomogeneous vehicles are absent from all of the traffic flow models, or almost all of them. There are probably a few ones out there on the fringes, but by and large, the fact that signals propagate at different streams, different speeds through different vehicles is not in the models that we work with. All right, so one more trick, and then we'll call it a day. I've got a couple more tricks up my sleeve, but those, maybe next talk I'll give you those tricks. So, high occupancy vehicle lane. To be in this lane, you have to, in this case, you have to have 3 or more passengers in your vehicle. All of these other lanes, you can have one person in your vehicle. So, to be in that lane, you have to have a special content of vehicles, and the logic for that is when this roadway is congested, and the roadway I'm looking at here is very congested, the more people per vehicle means the fewer vehicles per people. So this lane's going to move a lot more people during congestion, and that's what you want to do with your transportation system. So when your system is overwhelmed, all right, well, we're only going to be able to get so many vehicles through, but transportation isn't about moving vehicles, really. It's about moving either people or goods. Okay, we'll try and be more efficient, and we're going to give priority to the vehicles that have more people in them. So this is just using data from lane 1, the HOV lane, and we see during the non-HOV hours, we get this sort of triangular shape, whether it be flow occupancy or flow density, and then we project that into speed spacing, and we get a straight line. When the HOV lane is in action, we get this blunted curve, some people would call it a parabolic shaped curve, in the fundamental relationship. So, if you're a decision maker, you might look at this and go, well, that peak is higher than this peak, so that's a good thing and this is a bad thing. I'm sorry, that's a bad thing. We don't want the HOV lane because it's fewer vehicles per hour. Well, these plots are completely removing your temporal influences. So that's the first thing is, don't let the distortions of the plot throw you off. So let's come back here and again, and we're going to take, so this is already generated with a single vehicle passage method, but now we're going to add in one more wrinkle. So in addition to sorting by vehicle length and vehicle speed, we're also going to sort by the adjacent lane speed, lane 2. Or actually, we'll do the relative speed in this case. So when lane 2 is moving a little bit faster than lane 1, so between 0 and 10 miles an hour faster, we see lane 1, the black points just correspond to the black curve. So black and pink curve, I take those, go to this slide, and I just turn them into points. And all the high-speed stuff above 50 miles an hour, I'm just turning that off because it's a single vehicle passage method. You get confounding effects at high speeds. So I'm just looking at the lower speeds, and while the HOV lane is active, when lane 2 is moving faster, then lane 1 gives us this red curve, which is very similar to what we see when the HOV lane is not active in lane 1. Now when lane 2 is moving slower than lane 1, all right, now we're starting to pull down, so we're getting a lower flow for a given speed, and we see that also we're getting a larger spacing for a given speed, so just reading horizontally across. So this is from 0 to 10 miles an hour. We add in 10 to 20 miles an hour, so when lane 1 is moving 10 to 20 miles an hour faster than in lane 2, we get yet another curve that way, and so forth. So the higher the relative speed between lane 1 and lane 2, the more conservative the lane 1 drivers are becoming on average. So they're taking a larger spacing at a given speed, or perhaps they're taking a lower speed at a given spacing. Which way is causal? That's yet to be determined, and it's actually probably feedback, and both one impacts the other and vice versa. All right, now the amazing thing is, now that we know to go looking for that, when we go to the non-HOV periods, we actually see the effect is still there. So this is not simply because of HOV traffic, but it's just more pronounced when you've got the HOV traffic because you can sustain a differential of speed here that you can't sustain when you've got general flow vehicles in both lanes. So during the non-HOV periods, you can have single driver vehicles. So if this lane starts going really fast compared to this lane, the people in this lane are going to go, I want to be in that lane. So you get a feedback mechanism that keeps the lane speeds at least roughly close together. But that said, we still see going from lane 2 faster to lane 2 slower, we still see that same movement to more conservative when the adjacent lane's moving slower. And well, with the loop detector data, I don't have any quantifiable measure to explain why this is happening. I would suspect that's probably at least partially to do with the peripheral vision, where you see things passing by on the side of your view, and you become more careful as a driver. But whatever the cause, the adjacent lane speeds are also absent from most macro and micro traffic flow models. And I'm sure at some point Margaret will put her hand up and say, well, they are in these traffic simulation packages, and that might be true. But in the models themselves, they aren't in there. So that gets me to my closing. So again, even if you don't think about traffic flow theory, it's out there, it's impacting your life. If you're doing anything with surface transportation, at some point you are tripping over something that has to do with traffic flow theory. We got the problem in the field of traffic flow theory that loop detectors or things that emulate loop detectors are really our primary source of large quantities of empirical data. But the way the data are usually processed, so the processing that I was complaining about at the beginning, that works great for their primary deployed purpose. You're an operating agency, you want to know where your traffic's congested. Nothing wrong with those calculations for that. But if you're a traffic flow theorist who's trying to figure out traffic, there are so many confounding factors that it's impossible to really get too far. So just, taking a new approach to analyzing the data and aggregating it, we can get rid of many of the sources of errors. And those are some of the sources that I talked about at length already. And that gave rise to the single vehicle passage method that untangles those factors. And it gives rise to amazingly clean relationships. And from those, we can start questioning some of the basic assumptions and pull out new relationships that just simply aren't there in the historically entrenched point of view. So in this talk, we saw two of them. So vehicle length and reaction time are dependent. I can show you several papers that argue that they aren't. Well, assuming that they're independent, blah, blah, blah. Okay, well, guess what? You've built this castle in a swamp when you do that. And then the independence of adjacent lanes. Conventionally, you either say, let's take all of the data from all the lanes and we'll calculate flow across the roadway. Or you say, I will take just this lane, and what's my distance to my leader? That's what's going to, Both of those approaches, the conventional approaches, fail to recognize the dependence of adjacent lanes. So as long as these factors are running around there unaccounted for, they're going to confound any of your findings that you get and undermine the quality of your results. And so with that, I'd like to thank you for your time and take any questions.
Thank you very much for the presentation. We'll now proceed with the questions. Are there any? I have one. You mentioned about the distribution of speeds over time and speeds over space. How do those two techniques differentiate the results of the modeling procedure? And is the result significant on a macroscopic level, for example?
So the simplest way to talk about the difference between what you'd see over time and what you'd see over space is find a roadway where you've got parked cars. So if you just stood at a location and watched vehicles come by, you would see, okay, everyone's passing at the speed limit. But if you took two closely spaced photographs and you measured the speed, you'd both see the vehicles traveling at speed limit, but then you'd also see the parked cars on the side of the road, and you'd get a much lower speed when you calculate the space mean speed compared to what you'd see calculating the time mean speed. And so the real difference is how do you relate flow to density? Do you use the time mean speed or the space mean speed? And it turns out you need the space mean speed. So in more practical applications, it isn't you've got stopped vehicles and moving vehicles. You might have 60-mile-an-hour vehicles and 50-mile-an-hour vehicles, and so that the same factors are at work, but they're really clear-cut when you talk about parked vehicles.
Yes, please.
Can I make a comment rather than a question? It's sort of reflecting back. The early models were really constrained how to use models because we couldn't rely on detectors. The technology wasn't good enough, and therefore we were limited. And when we moved into the demand responsive control, when the loops were reliable enough, we were able to use the data, as you pointed out there, to develop local mathematical models that are associated with interpretation of specific data to, for example, change traffic lights in a speed system. As we have that real-time data available, the next step is to say, well, as a byproduct of this intelligent traffic control system, which in the early days was essentially a few fridges in a room, we started to build on that to use that data for other purposes. And that's where the interest lies, is how can you use data that's collected for one purpose to use it in another, for another purpose. I think in terms of demand responsive control systems, they've actually evolved and produced data to help us with those additional applications. I think where we are now, today, is that we can, to a certain extent, forget the use of traffic models for modeling what's happening now by interpreting the data that's coming through the system.
Well,
But I think, as you say, detectors will give you one perspective on what's happening on the road, flow, delay, fluid heat. If you need to use the data, if that data is limited, you have to find another means, which is through radar, video, and other methods. But then you have to process that data. That data has its limitations. So for me, moving forward in the future, we need a combination, an integration of different types of detectors to give us a rich picture to solve our problems today.
With these data, at the resolution for the single vehicle passage, you probably don't need that for real-time traffic control. But what you do need this for is, so you say, there are these models built up over the ages where you see conditions at this detector and you predict your conditions at the traffic signal maybe a block downstream. And that's true, and that's how you should use them in practice. But the nuanced evolutions, one of the things that this might show is you've got a dependency on lanes. So for example, when you look at arterial streets, first of all, I'm sticking to freeways here because freeways, limited access roadways, are so much easier to deal with than arterials where, the traffic might turn off or the traffic might turn on. On arterials, one of the things that you'll face that, an example where this might be applicable is you might have an underutilized lane, but if the traffic's still moving slow, how do those two lanes interact? And that's stuff that, I don't think has been fully explored because you don't have the microscopic data. Now, one of the things that, I've shown this stuff to traffic flow theoreticians, and even they don't point to this in, so can anyone see the glaring problem with these plots right here? Remember that plot I showed of the 30-second data? It's a big, ugly cloud of points. And that's really where the cutting edge of the research is so I'm doing a lot better job capturing the central tendency and explaining some of the variability. But you pick any one vehicle, these curves probably are not going to be representative of what that one vehicle is doing. And that's where getting, whether it be radar data or camera data or so forth, there's probably several PhDs worth of work going from this to, okay, well, how do you explain these cloud of this big massive cloud of points. And yes, so you do need other sources of data.